Okay, guys, as promised, I'm going to give you an outline. In fact, not much more than an outline. I think I'm going to go over exactly the way a report should look. Of course, you could do some different style considerations. The way I made headings here, for example. So it's not set in stone, but this I tried to include basically everything you would need. Okay, and also to notice this style of voice I use, this sort of dry / clinical voice that you're supposed to use when you write a scientific report. All right. Now just to make you feel better about this, first of all, this might make you feel a little worse because, first of all, I've got 10 pages here. And there's a lot more actually writing that has to be done in the analysis part here, which I didn't do because that part you already know sort of know how to do. But since now you'd say that's bad, but I'm going to say no, that's good, because when I posted on Canvas this file where I just deleted all the words I typed, and I left behind the equations and the figures I created today while I was making that. So let's see. Yeah, so here it is. Let's see. Oh, I put it in the wrong place. No, Lab 12. Yeah, report, figures, and equations. So as always, it's perfectly fine. What's nice is now these are actual things that can be edited. These are text Microsoft Word text boxes. What's nice about them is that you can put a picture inside and add a caption. In fact, you can use, let's see, where is design, is it? Yeah. So you can choose these format boxes here, and must be one for figures. But anyways, you have the possibility, and I'm not getting into it today, that you can define this like as a caption somehow, and then you can insert a table of contents, and depending, you would maybe define your own. And it uses all those stylistic choices from this. I guess they call this a style gallery here, but that's another day's lesson. I'm looking down here because the little wild man is chewing on my desk here. He's almost 4 months old. He's going to start losing his teeth soon, and so he's chewing on everything. And he's also kind of pissed off that Jenny left him. He's pretty attached to Jenny. Okay, anyways, let's take a look back here. So I wrote some kind of introduction, and we talked about it in class, so you can word it as you will. So we have so-called restoring force. That's also conservative. Now, by the way, I was thinking back over like the wording here, and it occurs to me that a restoring force probably is conservative, but I'm writing this as if I was you, and so this is what we kind of know, right? I mean, you're not expected to know all the deep nuance of calculus and that kind of thing, right? So, and also notice that I'm using terms without defining them, so I'm going to have to get to that eventually. And that's sort of why I put restoring force in quotes, for example. So in the presence of restoring force, that's also conservative. one can see the possibility of repetitive or oscillatory motion, right? So if I have something where I can push it out somewhere and it's going to come back, sort of like a pendulum, then I kind of expect that it's going to repeat, right? So that's repetitive motion. We're taking care not to exactly call it an oscillator just yet, but it's basically the definition. So we present the study of a hanging spring as an oscillator. Maybe I could have worded that a little better. First, we'll do a theoretical development to predict the expected behaviors. Then we'll present the experimental design with the procedure and then with data. And then we will go through an analysis of the data that showed that the spring shows not only oscillatory motion, but is indeed a simple harmonic oscillator. And again, that's up if you want to go that far. I suppose, strictly speaking, I didn't do such a great job in deciding what it was, but again, and for the purpose of an 1100 level lab, it's perfectly fine. So of course now I got to do a little definition. What's a conservative force? And so of course you can pause this video if you want to take a look. I'm not publishing these words in a form that you can copy paste them and turn it in. It's going to watch in case you to watch for that kind of thing. I'd like you to try to. It's perfectly fine to just take this and reword it in your own words, but I don't want you to simply copy paste. And let's see, keep going on restoring force. So first I talk about what's a conservative force, what's a restoring force, because there is a slight difference. Even though gravity will pull you back down, it's not exactly a restoring force because there's no such thing basically as a negative. I'm going to pause this because Jenny just came in and I don't want the little wild man to run out into the street. Okay, Jenny's got the Scout safely pulled into the driveway, and the Toby man is all happy that she's here. All right, so explaining, I was defining terms, then saying, we have this simple equation here for restoring force. I suppose I should have said something about it being for a spring. I never did, actually. And so then I made a little diagram, and just so you see the power of Excel, I just made a quick little diagram there for that. And figure XXX, okay, so in some place, figure so-and-so shows this. You have to play around with that. And so we see at x equals 0, the force is 0. X is less than 0, then the force is positive, etc., etc. So then I say, look, if there's a force somewhere, a net force, we can reasonably expect there's going to be an acceleration. So we write Newton's second law, then I explain the notation of x dot and x double dot. And then I do my manipulations. And, I didn't even get involved with if kx was positive, right? So, again, it only works if kx is negative. But, we're not calculus experts or linear differential equation experts. This is a second-order linear differential equation. It contains acceleration, that's why it's second order, and nothing squared or cubed, and there's all kinds of people writing books and books about it, but we're just going to try a guess. And so we're going to guess this, then I explain what it means, and then I said, oh, by the way, it's also the equation of a simple harmonic oscillator, and then I put a ref. So ref might be a Wikipedia article or something like that. So then I took this diagram and I just kind of stole it from the lab manual, but I doctored it a little bit. So just FYI, I got the Windows snipping tool where you see I stole part of another diagram. So you just say, okay, I want to steal a part of this, and then you can take that, and you have limited editing abilities in there. But what I do is it's a combination of Paint, a simple program, and then also one of the best ways to manipulate make diagrams is to use PowerPoint. Actually, it's pretty funny. I mean, I was taught that by my grad student colleagues a long time ago when we were making posters. See, I stole this diagram from I think Chegs or WebAssign. Then I added the words and the arrows, and then I just select everything, and then I copied it and I pasted it into a text box. And so you see how the text box works, right? There's the picture in there. That it's just nice to keep it, and it keeps it together. I mean, you can certainly paste a picture in and then put a caption, but you can't. They don't stay together unless you put them in the text box. And you can also, if you wanted to, let's see, we should be able to format this. Well, you can't read it now because, let's see, is this the outline or the fill? Well, when it'll go off the screen for you guys. Here we go. Text outline. So we want to look for shape. There we go, shape outline. So if we wanted to, we could get rid of the outline, right? It's not. We don't have to keep it. I just happen to keep it for now, just so. And in the file I saved, so you guys could easily understand what's going on when you look at it. And then you see there's other diagrams I stole. Then I brought them and manipulated them in Paint first, and then you'll see in a little while how I create the results in a little while. Okay. So, right. Notice I did a little different. I didn't use 2 pi f and 1 over t or 1 over f. I just said, hey, look, omega is radians per second. And so omega t, so I'm explaining equation 5. Maybe I want to move it so that maybe I lower this picture down a little bit so it's not it's not too far away from equation 11. Equation 5. And so I said, look, omega is radians per second. So if I multiply omega times t, I get radians. So then that is what we want, because then that means that, because cosine wants to see an angle, and then t is the time for delta omega times t, they equal 2 pi or 1 cycle, right? It's pretty obvious from the picture. And then I go ahead and I say, well, x dot equals this. This is where, again, ref, it's simply like a table of derivatives or something. This is actually, remember, I went through it. It's called the chain rule, but you might be able to look it up, or you could just eliminate ref. It's not the end of the world, but since, in physics 1100, and we're not supposed to know about calculus. So I went through the whole development. It's just a slightly different way than the manual. And what substitutions, then here again I showed, well, look, if t is the period for 2 pi, then if I multiply capital T times omega, it will be equal to 2 pi. So that allows us to express this like that, the period like that. And I'm looking at this and I'm thinking, oops, I want to get all of it. There we go. I want to make it a little bigger. Looks nicer. Okay. And so then we conclude then, if we arrange a system that obeys f equals negative kx, this system should behave as a simple harmonic oscillator with a period k. And the period of it will depend on k and m, on km, but not on a sub 0, not on the amplitude, because you see there's amplitude's not in there. And maybe you might want to put some words, like look in the figure, you can see exactly what amplitude means. And I just said, well, you know, cosine only goes from -1 to 1, and we can imagine that maybe amplitude is bigger than that, so we need a number to express that. And also, since cosine is dimensionless, I have to have something out front there to turn the result into meters, because I need the amplitude to be, this is x in meters. And also, again, keep in mind here that x is the y-axis here, and it's time on the x-axis. It gets a little confusing. Okay, so now procedure. So we got a spring. It's about, you know, it seemed like it was an inch or so in diameter. It was so long. I didn't take any pictures, and maybe that would be, pictures would be fine to put here. And we set it up on a chemistry stand, put a weight hanger, and we attached a meter stick. And then we had a stopwatch and a mirror to reduce parallax errors. And, you know, that is one of those things where you could take a picture of the mirror, again, the way you used it. It's not really absolutely necessary to explain what parallax errors in a mirror is. Most people, the audience is supposed to be a scientifically literate crowd, so you don't necessarily have to explain what parallax means in a report. You certainly should have some words in your manual if you did use the mirror. So our first goal, and in fact, maybe you would say you could list the goals first. Anyways, our first goal is to see if the spring doesn't obey equation 2, the F equals negative kx, because if it doesn't, all bets are off, right? We talked about this in class. So we talk about using gravity and how to change it into an equation that we can fit for a straight line. And I talk about why there's no more negative sign anymore. Now you might talk about why it's 1 over k. The reason we did that is because we have usually the x-axis on a graph is the independent variable. So in this case, that means the number of weights we put on the hanger. And the dependent variable is the result, and that's what we measure. We measure the stretch. Then I went into how the factors we use. For example, we needed to make sure that there was no, we wanted to start at a place where all the coils were separated. So I didn't have any pictures, so I just dug up something and chopped it up, chopped the top and bottom off, put it in there. And then I used the same picture, but I added in these arrows and the line to show how we measured it. And we did measure to the bottom of it, but I guess in the point of a report, you don't have to bother with that. So then we recorded L and plus minus L well, first we determined what? Some kind of mass. Yeah, we put enough mass on it just so the coils are all, has some non-zero separation. And then we recorded that mass and that length, and then we put on 3 more weights, and we recorded the length and a plus minus length. And I comment, you know, we didn't use any plus minus mass because, in fact, we used standard weights that had a known plus minus, a standardized plus minus. We didn't weigh them. We did, of course, we weighed them just to make sure that the numbers matched. But there's no reason to quote a plus minus on the mass because we didn't really weigh them ourselves, and the plus minus, the quoted uncertainty from the factory is so much smaller than any uncertainty in our measurement. We decided not to bother listing it. So I think this plus or minus 0.5 here, half a centimeter, might be, you know, it's not that optimistic, I guess. Then I talk about measured period as a function of amplitude, and I discuss the factors about, this is a really important paragraph. So make sure and pause the video and read it over carefully. It talks about how we chose various places, like the equilibrium position, how much is the amplitude, what is the amplitude, and about we want to make sure that the coils always stay separated even on the upswing, but we also don't want to bend the spring. And I used this. I stole this picture from a lab manual, and I eliminated a lot of stuff. And I show here's A0, and the amplitude is the start point, and of course the start point was always how far down we pulled it. I didn't get involved in mg being constant. I suppose we should have, but it's not the end of the world here. And then I show the data table. Yours should be different, because this, I think, could even be artificial data from a sim or something. And I explained about why we did it for a certain number of cycles. Of course, I didn't mention that we didn't go more than 5 or 6 or 7 cycles, because if it did depend on amplitude, we wouldn't be able to tell if we counted for too many cycles. That's up to you if you want to include that. What you could say is, look, we did so many cycles, and if indeed there was an amplitude dependence, we realized we'd have to go back and try varying amounts of cycles, for example, or something like that. But we decided, well, we'll do 5 cycles for now. And if we suspect there's some amplitude dependence, we'll go back and try something else. We did a quick sketch of this, and we didn't see any obvious amplitude dependence, for example. And then the next step was mass and period with different masses. Oh yeah, notice I said note the mass was fixed. You could say here, like, note fixed amplitude. This couldn't hurt. And this I just copy pasted from the spreadsheet. I pasted it as a picture even. It's probably a good idea to paste it as a picture instead of pasting it as text or have it linked to the spreadsheet. If you post it as a picture, it looks better, and then you don't have to worry about any conflicts coming up with the spreadsheet and the Word document talking to each other. And what's going on here, I guess, I don't know. Let's see. Somehow there must be, I might have added a page break or something here. I don't know. Yeah. Okay, well, that's sometimes you might do. I think because the word analysis before was on this page, and I didn't want it all by itself. I wanted it near. Okay, so this is the part where there's a lot less structure to what I've written, because this part we've been through before. Now in this case, I do have the complete data table here, and this is the, because there aren't that many data points, right? There's only the one for each part. So if I had multiple data tables for the same exact type of measurement, I would only put one here. And same as these data tables. There's only one for each measurement. And they're not really long. If there was like 30, 40 entries, I would just truncate it and just show an example of a few of them. So here then I've got all the analysis, and of course what in my case actual mass was the mass of the total, the hanger plus the weights. I said, okay, I'm going to subtract 50 grams from each one to make, so I have a 0, 0 intercept. It's not important to do that. Then I converted mass into newtons. Remember now, it's in the other videos that these are grams, so you have to convert those to kilograms. And then length was in centimeters, and then I turned it into stretch, the S variable, because there's the original, when I put the so many grams on it, that I just say that just was bringing it to all the coils being separated. So I call that mass equal to 0. And then that meant the stretch would be 0. So I would subtract 54.6 from these. And I converted it to meters. And then I did the error propagation to convert the plus minus centimeters into plus minus meters. That's all in the video. And then we have the column for fit, residuals squared, the chi-square, and then the data minus the average data squared. And you see there's other bits and pieces here, so you have to explain that. And then there's my graph. Notice this one I've pretty much formatted. I probably would get rid of these extra zeros at the end. I have a label for the y-axis, label for the x-axis. I have a legend, I have a title, and I got error bars, explaining what's plotted. Then I have my fit parameter table, so you have to explain about what r squared is, why we care, what's r squared all about, right? That's important. Now, somehow, oh, you know what? Strength. Oh yeah, never mind. This is, of course, we don't expect a non-zero slope because this is not the amplitude. Thought I did this in the wrong order. So now I have a slope. I have a max-min slope, right? And that's you have to explain what that is. It's simply you simply varied the slope so that the chi-square went from its minimum value to +1. And then we got a maximum of the slope. Then we could determine a plus minus. Then we have the 4 pi squared, I guess, whatever. No, not in that case. It's just 1 over. 1 over the slope equals k. And then you can use you have the plus minus slope. You can turn that into plus minus k. Again, that's in the video. And we see that our plus minus divided by our measurement times 100 is 2.4%, so we feel kind of happy with ourselves. So thus we conclude that the spring does obey this, and also our r squared is also very close to 1. So the r squared test tells us that we used a linear fit, and it is a linear fit. I mean, normally, before this, we used to just say, well, the chi-squares, the sum of the chi-squareds was fairly low, but now we have an actual number and say, look, as long as the r squared is very close to 1, then we know we have indeed a set of data that obey a linear equation. So now it's time to do period as a function of amplitude. So now I've got the original data and then all the processing I did to it. And then there's our plot. It's really not enough data points. And then the fit parameters, and then, we say, look, the slope is so tiny, it's effectively 0. And the y-intercept, of course, let's see, the y-intercept, I did it in the video. The y-intercept actually ends up being the actual period of that particular spring. If you set things a certain way. Oh yeah, and then the r squared. Now this data is most certainly artificial. So we ended up with a negative r squared. And I haven't seen anybody's data. No, I haven't gotten anybody's data to test to see exactly what's happening with the real data in r squared. And also you see the relative slope is, the relative error on the slope is pretty small. I mean, that's ridiculously tiny. So this is artificial data of some kind. And now at the end we got period as a function of mass. So I went through the manipulation of this so as that to show why we did it. And with the slope, we expect the y-intercept of 0, but this may not be true because we ignored the mass of the spring itself. So you have this somewhat more complicated looking table. Explain the table. And there's our graph. Quite nice and pretty. We have our fit parameters. And then we say, we conclude that T versus M predicted is correct because the r squared value is basically 1. I mean, look, 0.9994, so it's a straight line. And our relative error, it's only 2.8%. Of course, now we'd like to, we'll comment on, I don't know if you guys weighed the spring. I don't know if we talked about weighing the spring, but you could comment on the non-zero y-intercept. It means simply look in the lab manual, and there's a little mention of it. And then we compare the k from before to this k, see how close they are. And basically, the summary is, we repeat what the conclusion from each of the parts, so they're all in one place. So we concluded this because of that and that. Remember, you always have to, don't just say it shows this or it shows that. You have to say it shows this because, right? So this table shows that the equation for the mass, the period as a function of mass, or at least the period squared as a function of mass, is for sure a linear equation because the r squared value is so close to 1. And we were able to extract a value for k that's very close to the value of k we measured independently. So we conclude that this we believe this, or somehow like that. That equation is correct. And then you just summarize it. And like I said, look, the relative errors we got in each of our measurements were all less than 10%. So we're basically pretty happy that we did a good job, and we don't really have to go back and redo it within the limits of the crude apparatus that we have. We feel like everything is cool. Okay, I guess that's it.
Yeah.
All right, it's going.
Okay.
All right, guys. So just so you can get an idea, I think I showed you guys Toby before. So he's not quite such a little guy anymore. He's getting there. Here, I'll let Jenny get in the shot better.
No, that's okay.
Oh, that's okay. Anyways, yeah, the little wild man is not quite so little anymore. So hopefully that made you smile. And I'll see you all soon. Dopey thing.